be back with you. This video clip is about how to calculate a load-shear-moment diagram when you have a distributed load, and it's not simple like a constant load across the beam. Here's the problem right here, and it's inspired by a little airplane called a VP-1. This was designed a while back for people who want to build their own airplanes, and the structure is very simple. The structure, as I've got represented here, is a single beam. It's actually wood in real life, and it's pinned at one end. It's actually pinned to the fuselage, and there's a strut coming in at an angle. Now, in the real airplane, it's not 45 degrees. This one it is. It's 45-degree angle, and this strut is in compression. Okay, that's what holds everything in place. And of course, there's a distributed load along the spar that represents the lift. Now, theory says, and in practice it's really true, the lift is approximately elliptical as you go down the wing. Well, an ellipse is kind of an awkward shape to work with for what we're doing here. So I thought I'd go ahead and break this down into a rectangle and a triangle. That's approximately an ellipse. Now, I've also done everything in terms of in English units. Now, the reason I did this is I've assigned this problem to my class as well, and I defined everything in English units because the original plane was designed in English units. If I had to do it from scratch, I'd probably do it in metric units, but I want to keep it consistent here. So if you're not comfortable with English units, I apologize. Now, the plane is assumed to weigh 800 pounds maximum, and I want to be able to pull 5 Gs without overstressing the wing. Now, that's an awful lot, but that includes a safety factor. In order for that to happen, the area there plus the area there has to be 200 pounds, and that works out to a height here, this distributed load height, of 19.048 pounds per inch. Okay, so the goal here is to draw a load-shear-moment diagram. Probably what's going to happen is in the first clip here, I'll get as far as drawing the load part of it, then I'll stop, and then we'll do the shear and the moment part in the second clip. Okay, so in any kind of problem like this, strength of materials problem, you always want to start with a free body diagram, right? Okay. In fact, if you don't start with a free body diagram, you ought to be asking yourself, why am I not drawing one? You better have a pretty good reason. Don't have a good reason. So let's start with a free body diagram, and I'm going to start by drawing just the beam. We're going to draw the free body diagram about that. Now, the wing is 120 inches long, and that break point right there is 90. And then the pin joins on a point B here, which is 24 inches, and it's also 24 inches there. So that's a 45-degree angle. So let's start putting all that stuff in there. Well, the beam we already know is going to be in compression, so it's going to be pushing down that way. It's going to be in compression. That means I'm going to have a horizontal load. We'll call that Bx, and a vertical load. We'll call that By. And I'm also going to have a reaction force here at the other end, okay? And I'm going to call that Ax because it's got to be equal and opposite to Bx. And I don't know which way Ay is going to go, but I'm going to draw it up. If this turns out not to be the right answer, if it turns out to be going down, Ay will just have a negative sign on it. And of course, I also have to draw the distributed load. Now, because I'm only trying to find the reaction forces at A and B, I can concentrate this load and put it at if I put it at the correct point, I'll get the same answer there and there. Remember, the reaction forces, those pins at A and B, and they really are pins, they're just bolts that go through fittings on the plane. Those pins right there don't know the difference between a distributed load and a properly chosen, properly located concentrated force. It looks the same to them, right? Now, the beam knows the difference. The beam definitely knows the difference between a distributed load and a concentrated load. The reaction forces don't know the difference. So, because of that, let's go ahead and use a simplified representation for this distributed load. Now, if you take 90 inches times 19.048, you get, I want to make sure I get this number right, 1714.3 pounds, okay? And it's going to go at the centroid of that. What I'm doing is I'm dividing this concentrated load into a rectangle and a distributed load into a rectangle and a triangle. So I'm going to have two concentrated loads. One at the centroid of this, which is going to be at 45 inches. Okay. And the other one, which is going to be the centroid of that triangle. The centroid is a third of the way in from the one of the ends. So that's going to be 90 inches plus a third of that, so that makes 10 inches. So at 100 inches out, okay, if that's 100 inches out from point A, I'm going to have the second concentrated load. The area of that is 1/2 BH. Well, base is 30 inches and the height is 19.048 pounds per inch. So the units work out. This will be pounds. And this works out to be 285.71 pounds. Okay. Now I have everything I need to know. Okay. I have, let's see, 1, 2, 3, 4 unknown forces, and I can only write 2 equations of equilibrium, can I? Well, I can write 3. Seems like too many, doesn't it? 4 unknowns and 3 equations of equilibrium. Well, I already know what that angle is, so since this is 45 especially, I know that Bx equals By. So there's my fourth equation. All right, so let's start by maybe summing the moments about A. And that has to equal 0, right? I mean, what that'll do is that'll tell me By directly. If I sum the moments about there, the arm for Ax and Ay is going to be 0, and the moment arm for Bx is also going to be 0. So that'll give me an equation that only has one unknown. That's nice and convenient. So I know that, let's see, there's my assumed sign convention. So By is going to give me a negative moment. So negative 45 inches times By plus, 24 inches, make sure I get that right, plus 45 times 1714.3 pounds plus 100 inches there, times 285.71 pounds. If By is my only unknown, so when I work that out, I'm going to get By equals 4404.8 pounds. I'm using my cheat sheet here in case you want to know why I'm looking down. I don't trust myself to try to remember all these numbers. So there's By. Okay, well that means that has to also equal Bx, right? Because we know we've got a 45 degree there. Just drop my cheat sheet. Okay, so we know 2 of our 4 unknowns. Now it's time to find Ax and Ay. Well, let's see. Let's try maybe summing the vertical forces. That's a good thing to do. So I can say the sum of the forces in the y direction equals 0. Well, let's see. Those had better add up to 2,000 pounds. And I know that's 4404.8 there. So let's see. 2,000 pounds up minus 4404.8 plus Ay equals 0. Okay, well, I got the 0 over there. Well, that's going to be a negative number there, and that's plus Ay. So if I solve this, I get Ay equals 2404.8 pounds. And that comes out positive, so I've got that in the right direction. We're good to go now. I've got, let's see, Bx, By, Ay. What about Ax? Well, there's only 2 horizontal forces, Bx and By. I know they have to be equal and opposite. So I get to go ahead and here and write Ax also equals 4404.8 pounds. So I've got all that good information there, and I'm ready to start drawing a load shear moment diagram. I've got a small board here, so what I'll do is I'm going to erase this and I'm going to start the load shear moment diagram over there. Alrighty? If I was smart, if I learned how to use my video editing software, I'd cut this part out so you don't have to look at the back of my head. There you go. That's a pretty good start for the load shear moment diagram. I'm going to draw the load there. The loads are easy. I know I've got, let's see, 2404.8 there, right? Now, there's negative force. I always put the negative forces going down below the line. I know it takes a little more room, but I mess up a lot less often when I do it this way. And that's 4404.8, also in pounds. Now what else? Got the distributed loads. Now, I can't use the equivalent concentrated load anymore. This beam does know the difference between a concentrated load and a distributed load. So the distributed load goes out here like this and then goes down. And this is as before. Okay, that's 19.048 pounds per inch. That's of course in pounds, and that's also in pounds. So there you go. There's the load diagram. Now if I'm going to draw the shear diagram, put it right there. Okay. Now I have to do some more calculations. I'm going to stop right here since I'm about 10 minutes in, 11 minutes in, and I'm going to pick it up in the next video clip, okay?